Hi everyone, welcome back to the Technion's ECE Deep Learning course. I'm Tal, and in this tutorial, we are going to discuss several training techniques in deep learning that help us enjoy stable training and converge faster. So let's begin. Okay, so we begin with a concept we are already familiar with from classic machine learning, and that's normalization or feature scaling. And it's a fundamental part of the data pre-processing stage. It can improve the performance of some machine learning algorithm, but it may also harm others, but usually it improves. And it is especially important for gradient descent-based algorithms such as linear regression, logistic regression, and of course neural networks. We will see an example in a minute. And the idea is that the range of features significantly affects distance-based algorithms such as KNN-SV and K-means and even PCA. And we want to make our algorithm agnostic to the scale. And remember that the scale of the feature does not imply that its importance. So features of larger scale doesn't mean that they are more important for the task we are trying to achieve. So let's take a look at the general formulation of gradient descent for linear regression, for example. And what we can see is that our update rule, it involves the original features, so x. And it, of course, will affect the effective step size of the gradient descent, because if the scale here is larger, then the effective step size we take in the direction of this certain feature, of this jth feature, then it will be larger. Okay. Now, the difference in the ranges of features can cause different step sizes for each features. That means that we can reach different minimas. So to ensure that the gradient descent moves smoothly towards the minima and that the steps of the gradient descent are updated at the same rate for all features, we need to scale the data or normalize it. Now, what we see in practice is that when we use scaling with gradient descent-based algorithm, then we converge quickly and the training dynamics are more stable. And this is important, especially when we train large neural networks. So remember, the scale does not imply the importance of the feature. Okay, so normalization. It is a scaling technique in which we normalize between some range, so usually 0, 1. It's also called MinMax scaling. So the idea is that we calculate the maximum feature value and the minimum feature value from the trained data. And then we just normalize all the features according to these values, right? Now, when should we use this kind of normalization? Then, in general, you should use it when your data does not follow a Gaussian distribution. So, for example, natural images, so the pixel distribution is usually not Gaussian. But it can also be used for other algorithms such as KNN and of course in neural networks. So for example, when we work with images, recall that we use the 2 tensor transformation, and it took the pixel values between 0 and 255 and normalized them to 0, 1 to float numbers. Now, for some architecture or tasks, so for example, GANs or diffusion models, sometimes it's useful to use symmetry and normalize to -1 and 1. So keep that in mind. Basically, you only need to add the transformation to -1, 1 if you want to have symmetry. Okay, the next type is standardization, and it is a scaling technique where the values are centered around the mean with unistandard variance. And this means that effectively we actually take the mean of the features to be 0 and the effective one, and basically we have the unit standard deviation. So the formula is it's like this. So we take the empirical mean and the empirical standard deviation and apply them in this formula. Okay, now in this case, the values are not restricted to a particular range. Okay, and it's very useful in cases when we know that the data follows a Gaussian distribution. But of course, it can work otherwise. And now, unlike normalization, standardization does not have a bounding range. So even if you have outliers in your data, they will not be affected by standardization because we do not squish the range of the features to be bounded, right? Now, in practice, there is no rule. Use whatever works best. Okay, you can always start with standardization, see if it works, then change to normalization, see if that works better, and use whatever works best. Now, it's a good practice to fit the scaling on the training data and then use the parameters of this of the training data to normalize the test data. We do this to avoid any data leakage during the model testing process, and also at test time we actually might get a single sample. So of course, a single sample we cannot compute its mu and sigma because we don't have them, and we need to use some learned statistics. So basically, we need the scaling parameters from the training data. Now, what about the target or the labels? So in case of regression, scaling of the target values is usually not required, but sometimes it may help with the scale of the loss, which can help having stable training dynamics. So keep that in mind. You should use some scaling on the labels if it works better and if the training behaves nicely. And otherwise it's not required. Okay. So we talked about scaling the input data, but what about in between the layers? What about normalization of activations? So it turns out that the key to stable and effective training of large neural networks is actually normalizing the activation. So in between the layers. The problem with that is that we cannot apply the same standardization or normalization we talked about with regards to the input, because at train time we are using different batch sizes, and since we apply the normalization on learned activations, these statistics will change in each iteration, and we can't calculate it on the entire dataset because we work in batches, so we can't apply the same techniques, so we need to do something different. Now there are two families basically of layer normalizations. We first cover batch normalization, or BN, which is different from the rest of the normalization because the other normalization, they do not operate on batches and they normalize activations of a single sample, and making them suitable for cases where we can't use large batches or even recurrent neural networks. So batch normalization tries to estimate the same idea we did on the input, the same standardization or normalization we did over the input, where we had access to the entire dataset. But since we are working with batches, we can only try to estimate it when we apply it on activations, on learned activations, which change in each iteration. So batch normalization, it works really well for when you have large batches. And it's basically what we see in practice, that it improves the convergence speed and the performance and the stability of deep neural network. The reasons, so there is a great debate why it works so well. So you can take a look at the literature and take your favorite and adopt the favorite reason. But in practice, it works, and that's what's important. Now, there is a cost to applying normalization in between the layers, and the first one is that we have usually more parameters because we introduce some scaling and shifting parameters. I'll talk about it in a minute, but it also involves more computation time because we need to compute the statistics of the activations. Okay, so how does this work? So let's formalize this. So we have our input to the layer. So it's X and it's N by D. So N is the number of the batch size and D is the features dimension. And we are currently doing batch norm over 1D data. We have learnable parameters, so scaling and shifting, gamma and beta, and they are both of the same dimension of the feature. Okay. Feature dimension, and we have the intermediates, mu and sigma, which are calculated. So basically we calculate the mean and standard deviation of each feature over the batch dimension. Okay, so this is why mu and sigma are of the same dimension as the feature dimension. and the normalized output of this layer is of the same dimension. Okay, we do not change the dimensions. Right. Okay, so in PyTorch we have 1D, 2D, 3D instances, and we will see an example in a minute. So how does this work with 2D input? So for example, images where we have batch size, channels, height, and width. Okay. So the idea is that we are going to perform batch normalization channel-wise over the channel dimensions. So gamma and beta, the scaling and shifting, are going to be of the same number of channels, right? And I'll show you in a minute how we actually do this in practice. So basically we consider the batch dimension and the height and width. So basically when we perform the normalization, we end up with something of size of shape C. So just the number of channels. Okay. So batch norm behaves differently during training and evaluation. So model.train, the batch normalization parameters are calculated over the batch. So mu and sigma are calculated over the batch. And at the inference time, we can get batches of different sizes, even a single sample. So batch norm has to behave differently. So we actually use the learned mean and standard deviation, which are running statistics. And this is a technique to estimate the global mu and sigma. Now, the way we do this is a technique we already became familiar with when we talked about optimizers. So it's called the moving average. So basically, we are calculating the new mu and sigma by using a momentum parameter, which is usually 0.1. So we take 0.9 of the old value and head 0.1 from the new value, so from the current batch, right? And basically, this should stabilize as we see more and more examples and as the training progresses. And hopefully this mu will be a good estimation of the global mu of the entire data, right? Now this is critical because we are working in batches. So the same arguments we had when we talked about optimizers applies here. Now it's super important to understand it because at inference time we might get batches of varying sizes, so we can calculate mu and sigma over the batches because we don't have a batch. So in the extreme case of a single sample, we just want to classify a single sample. We need to use the mu and sigma which were learned or estimated were estimated at train time, right? So how does this algorithm work? So it's very simple. So the input is just the x. We calculate the mean over the empirical mean over the batch dimension. Similarly, the standard deviation. We normalize, we perform the standardization formula, and we add a smoothing parameter epsilon in the denominator, right? So making sure we are not dividing by 0. And then we apply scaling and shifting. Now, scaling and shifting are learned parameters, so just weights, and you can actually turn them off by setting affine equals false. Okay, but by default they are turned on. Right. So let's see an example of how it works. And specifically, we'll take the case of 2D because it's a bit more complicated, but we'll see how we can implement it ourselves. So our data is batch size of 2, right? And we have 3 channels and an image of resolution of 8 by 8. Then we we create an instance of batch normalization. Now, in this case, the input is the number of channels. Now this is important because the learned parameters, so gamma and beta, are going to be of the same dimension of the number of channels. So we are going to have a shift and scale for each channel. And we set here momentum equals 0 and track running as false just for the sake of seeing what happens, but usually their default value is 0.1, and we track running stats in order to be able to perform inference on single samples or batch sizes or different batch sizes. So this is what happens when we apply a batch norm 2D. Now, we don't actually care about the values. I just want to show you that when we implement it by hand or by ourselves, we get the same result. So what happens under the hood? So we have our data. So first we need to calculate its mean and variance. So the way we do this is just by taking the mean over the batch dimension, height dimension, and width dimension, right? So basically we calculate the average channel. Similarly, we do this for the variance, right? And we have this smoothing parameter, which is by default 1e minus 5, similarly for batch norm 2D. And we perform the the standardization formula, and what you can see here is that we get the same values as here. So our implementation is correct. Now, what is important to see is that the mean and variance are of the shape of the channel. So basically we have the average channel. So the average red, the average green, and the average blue. Great. And it works really well usually, but there are cases where it doesn't work well. So let's understand when we should use batch norm and when not. So ideally, we would have wanted the global mean and variance to standardize our data, just like we did on the input. So on the input, we have access to the entire data set, and the input does not change over time because there's nothing learned there. So we could do this global standardization or normalization. But between the layers or inside the network, the activations constantly change between iterations because the weights are updated. And we work on batches, so we don't have access to the entire dataset. So if we were to calculate the activations for all the data at once, so of course we have memory limitations and we can't fit the entire dataset on the GPU. So it's expensive and we can't do this. So the idea is to use mini batches to estimate it. And this brings us up the reasons why when it wouldn't work. So for small batch size, if the batch size is 1, the variance is 0, so batch normalization cannot be applied, of course. So if you can train your model only with a batch size of 1 because of memory limitations, then of course you can't use batch norm. Now, slightly larger mini batch sizes won't have this problem, but small mini batches make our estimate very noisy and they can negatively impact training. And I'll show you this in a graph in a minute. Now, this means that we actually have some hidden lower bound on the batch size we can use. Now, a good rule of thumb is that the minimum batch size to use batch norm is 64. So if you have batch sizes lower than 64, then maybe batch norm is not a very good idea. Now, there are other cases where we can't use batch norm or we definitely shouldn't. So for example, RNNs, right? So of course, we now the data is not IID, so each sequence we have independent features, right? And of course, it's problematic to normalize by the time steps, so we need to consider different approach. And of course, we don't have access to the entire, specifically in RNNs, we don't have access to the entire sequence until we reach it. So we recall that we work in iterations, and in each time step we need to normalize. So how do we, what dimension do we consider? So it's a bit problematic for RNNs, and usually what we do is use layer normalization. I'll talk about it right now. So layer normalization. So maybe before we talk about layer normalization, I want to show you this in an image, right? So here is batch norm. So each cube here is a pixel. And we have the batch dimension and the channel dimension. So batch norm considers the average channel. So we consider all the pixels, right, in each channel over all batches, right? So this is what batch norm is doing. This is what is considered for the normalization operation. Now layer norm. So layer norm is a technique that applies the same standardization formula, but the dimension is different. So how does this work? So we normalize across the feature dimensions. So it's best depicted with or illustrated with an example. So the formula is the same, but the dimension is different. So let's say we have these 3 examples. So the batch size is 3, and we have 6 features, right? So batch norm will calculate the mean and sigma for each feature over the batch dimension. Right, so we can see right here. So this means that mu and sigma are same for all the trained data because mu and sigma are of the same shape as the feature dimension. So if you have 6 features, then mu is also has 6 features, and sigma is also 6 features. So basically, we have like a mu and sigma for the entire data. Now in layer norm, we calculate the normalization per sample. So for each sample, we calculate a single scalar mu and sigma. right? So we end up where the shape of mu and sigma is the same size of your the number of data, so the size of the batch. So if you have 3 examples, then mu and sigma will be of dimension 3, because for each sample you have the mean and sigma, right? So the dimension is different. Okay. So this is the idea of learn, and similarly we have the scaling and shifting parameters. They have the same meaning here. Okay, so when do we use learn? So we can use learn on every dimension that we want. So basically we can consider all of the dimensions. So for example, on images, we can consider all the dimensions. So in contrast to batch norm, where we considered NHW, here we consider CHW, so per sample. But this does not work well in practice, so we don't use it on images. However, we do use it in sequential models, so RNNs, and we saw it in transformers. So the idea is that we are going to normalize over the embedding dimension, which is just the last dimension, right? So the input to the learn is the embedding dimension, and of course we are going to have gamma and beta and gamma for each feature in the embedding dimension, right? So this is how it works. So in image, it looks like something like this. So we consider all the pixels and all the channels in each sample. So this way we don't have dependency on the batch size. Okay, so in practice, we usually use this. We usually don't use this on images, and it's good for sequential models, and we've seen this work quite well in transformers. Okay, the next type of normalization is an extreme one, so it's called instance normalization, and the idea is very similar to layer normalization. We consider a single example, but we compute it per channel, right? So we normalize across each channel in each training example. Now, instance normalization is specifically designed for certain tasks, so for certain visual tasks, for example, style transfer. And the problem it tries to address is that the network should be agnostic to the contrast of the original image, and it's better utilized in CNNs rather than RNNs. The equations are same as before, but the dimension is different. So let's take a look at instance normalization. So very similar to learn, we consider a single example, but we normalize over we consider the pixels in each channel alone. So each channel has its own normalization, right? So we do not consider the entire channels for the normalization. Now, traditionally, instance normalization does not apply the affine transformation, so no gamma and beta, but we can turn them on or turn them off as we want, and whatever works best. Now, the last normalization, which I like the most, and it's a trade-off between layer norm and instance norm. So basically, we can, instead of considering all the channels or just a single channel, we can just consider a group of channels. So basically, we can take a look here. So we can define a group of channels and perform the normalization per group. Now, as it turns out, group normalization is a very good estimation of batch normalization, right? But without a dependency on the batch size. So this is very desirable, right? Now, of course, the formulas are the same. Now the gamma and beta are learned per channel, right? And definitely similar to what we've seen before. And let's see an example. So, and it works really well in practice for images. And I'll show you in a minute a comparison to batch normalization. Okay, so let's see an example. So we have a batch size of 20, 6 channels, and 10 by 10 image. Now we can put all 6 channels into a single group. So basically, we want one single group, and we have 6 channels. So this is like using learn. And we can actually separate for 6 groups. So this means that each channel is normalized on its own. So this is equivalent with instance normalization. And we have the in-between, which is, for example, in this case, 3 groups. So this means 2 channels per group. So each 2 channels have their own normalization statistics. And this is the in-between, right? Now again, the normalization do not change the output dimensions. So though layer normalization and instance normalization were both effective on RNNs and style transfer respectively. They were still inferior to batch normalization for image recognition tasks. So what we're going to do now is understand when should we use each normalization. So group norm was able to achieve much closer performance to batch norm with a batch size of 32 on ImageNet and outperform it on smaller batch size. So group normalization is very attractive because today we have very large networks, so we cannot utilize large batch sizes, but we still need or want to normalize the activations. So a group norm is the way to go because it is agnostic to the batch size, which is good. And it's very close to batch norm in performance, but batch norm can outperform it for certain batch sizes. I'll show you in a minute. Now, what about layer norm? So as I've said, layer norm is good for sequential models, but because one of the implicit assumptions that layer normalization makes is that, for example, in images, if we apply layer norm on images, then all channels are equally important when computing the mean. And this is not true usually. So this is why group norm might be a better idea. And this is especially important in convolutional layers, okay? And basically, group norm has an advantage in this case. Now, if you compare group norm and batch norm, you can see that batch norm is significantly affected by the batch size. Right? So we can see that the performance largely vary between batch sizes, right? And group norm does not have this problem. Now, the final performance of batch norm with the optimal batch size might be a little better, but if you want something that is agnostic with a very slight slight cost in performance, then group norm is the way to go. You can see here that given the size of the batch, group norm is quite agnostic, while batch norm is significantly affected. Right. So the lesson from here is that usually group norm is the way to go when you cannot utilize large batches, and batch norm might be used if you can utilize large batches. Usually 32 or 64 are the lower bound for batch norm. Another problem we are going to talk about is vanishing and exploding gradients, and how we can solve this. So training a neural network can become unstable given the choice of your loss function, and of course all the other hyperparameters such as learning rate or even the scale of the target variable. And sometimes there are two common phenomena that can happen, especially with sequential models, so RNNs. One is vanishing gradients. So we discussed this when we talked about RNNs. We analyzed the gradients and we analyzed the computational graph, and so what happens with a lot of matrix multiplication. So we saw that sometimes we have a large power for a certain weight matrix, and given the eigenvalues of this weight matrix, we can either the gradients can vanish, or we can either explode because the eigenvalues are larger than 1, and when taken to a large power, then it can diverge. So vanishing gradients, when using certain activation functions, so for example like sigmoid in very deep neural networks, they squish a large input space into a small space between 0 and 1. So a large change in the input of sigmoid function will cause a small change in the output, and the derivative can become smaller and smaller as we go backwards in the backpropagation algorithm. The other direction, so exploding gradients, sometimes we have large updates of the weights, and it can cause numerical overflow or underflow. And the problem is more common in RNNs, right? We talked about it. And in practice, what you'll see is none or inf in your losses and the gradients. This means something does not work. Now, usually before we jump to any solution, the first things to try to alleviate it is use normalization. So if you don't have normalizations like layer norm in your RNN, maybe try to use it and see if it changes anything. And another direction is lowering the learning rate, because because maybe we are taking too large steps, and this can lead us to divergence. So make sure it's not the learning rate or a normalization issue. And if it's not, then maybe consider the solutions we are going to talk about now. So, okay, so the vanishing gradient problem can usually solve by changing the activation functions or using skip connections. I'll talk about it in a minute. But for the exploding gradient problem, a common and relatively easy solution is just to change the gradient before you take the step. So basically, we are going to clip the gradients, and the way we do this is it's called rescaling and clipping. Right, and together they are called gradient clipping, and the idea is that we are going to calculate the gradient norm, and if it's above a certain value, then we just clip it to the maximum value, right? So it's a very simple technique. Now, this actually biases the training procedure, since the resulting values won't actually be the gradient of the cost function. So remember that the gradients are comprised of magnitude and direction, right? So when you clip the gradient scale, then maybe the direction will be correct, but it's not the actual gradient. So we can see in this illustration here what happens. And it might be worth to have like a biased gradient if the training is more stable, right? So it's a trade-off, and it's up to you. And if it works, then use it. Now, the way we do this in practice is we have a function for this in PyTorch. It's called clip by gradient norm. Now, this is going to be an in-place operation. This means it does not create a copy in memory. We just go over the entire gradients and clip them if they are above certain value. Now, usually in PyTorch, in-place operations are marked by this underscore here at the end of the function. So here's an example. So choose your clipping value. It's a hyperparameter like anything else. So this is a good range to try, but of course it can be also outside of this range. You need to find it. Now we change our normal recipe and in order to include this function. So let's go over it. So the first steps are the same. So we do the forward pass, we calculate the loss, we zero out the gradients from the previous steps, and then we calculate the gradients. After we calculate the gradients, so after this line is called, then all the grad fields, the dot grad fields in our tensors are filled with values. Now we are going to go over them, right? So we're going to go over the entire model dot parameters and clip the gradients that are above a certain threshold, right? Then after we clip them, then we apply the optimizer step. Okay, so this incurs, of course, another computational cost, right? Because we need to go over the entire gradients and check if each one of them is greater than this threshold. But sometimes it can help us stabilize the training dynamics, and it might be worth it. Now let's talk about the other directions. So vanishing gradient. So how can we solve this? So it's not only for solving the vanishing gradient problem, but it's a general idea that found out to work really well and help us converge much faster. So skip connections. The idea is to skip some layers in the neural networks and feed the output of one layer as the input to the next layer instead of only the next one. So basically, we are going to propagate forward the pre-activated input. Now, we're going to talk about several types of skip connections, and it's quite popular these days, and we've already seen it in transformers, right? We did the skip connection, so we had the add norm blocks, right? Now, by using a skip connection, we provide an alternative path for the gradient with back propagations. I'll show you this mathematically in a minute. And it's experimentally validated that these additional paths are often beneficial for model convergence. Now, it can help us mitigate the vanishing gradient problem when the gradients become very small. And there is also another idea that makes skip connections very logical. So for visual tasks such as semantic segmentation or optical flow estimation or even classification, there is some information that was captured in the initial layers that we would like to preserve and allow the later layers to also learn from them. So if you recall, when we talked about CNNs, we showed what happens or what the activations look like as we go down in the network. So basically, when we go down, we extract higher level features, right? Or lower level, depending on how you look at it, and the information can become too abstract, and we never propagated the output of the previous layers to the classification head, right? So maybe there's some information that was captured when we operated on larger resolutions that we want to preserve somehow. So the way we do this is by using skip connection. And in CNN specifically, it's been observed that in earlier layers, the learned features correspond to lower semantic information that is extracted from the input. And if we do not use skip connections, then we just use the standard way like we did before, then the information becomes too abstract. So there are two fundamental ways that we can use skip connections, and one of them is addition and the other one is concatenation. So addition is related to the residual architectures, so residual networks, and concatenation is usually used in DenseNet and UNet, so we'll talk about them as well. Okay, so for ResNet, so the core idea is to backpropagate through the identity function by using a tensor addition. And the gradient would simply be multiplied by one of its values and will be maintained in area layers. So it's very simple. So here is an example of what happens. So basically you have X, you input it to the residual layer. So you apply some convolution or anything, and then you just add the input to the output, right? And this is also called short skip connection, right? And we do not change the input and output dimension. So basically, if we use convolution, then we usually use a convolution of type same. Now, mathematically, what you can see here is that when we take the gradient, we actually have the identity function here. So basically, even if this part is vanishing and go to 0, this part remains the same. So it allows another path to the gradient to flow. And basically it can help us alleviate the vanishing gradient phenomenon. Right. So in PyTorch, you can take a look at the full example here, but here's an example of a residual block. So it's usually comprised of two convolution layers, batch norm and activations. So of course you can change the activations and the normalization. So the batch norm can be replaced with group norm, and the activations can be changed to swish or whatever you like. And we also need to consider cases where the number of input channels does not equal the number of output channels. And in this case, we will just need to increase or decrease the number of channels of the input. So basically, you can see how it works. So you preserve the input, you apply the layers, and then you just sum with the output, right? So this is the idea of residual networks. We can now stack many residual layers to create ResNet. Okay, the second type of skip connection is concatenation. So for many tasks, there is a low-level information shared between the input and the output, and it would be desirable to pass this information directly across the network. And the alternative of addition is concatenation. So what we can do is just concatenate every output to the input. And this means that we will have a very large feature channels and growing as we progress in the network. Now the idea is to ensure maximum information flow between layers in the network, and basically we just concatenate each output to the previous input. So the number of channels grows as we go down, right? And this means that we can't have very large or very deep networks because the number of parameters will explode. So usually dense nets are not too deep, but they are very wide. So the input channels grow a lot as we go down. So this is the idea. So we just concatenate over the channel dimension, right? So this is why we have a growing number of channels as we go down. The other type of concatenation-based skip connection is UNet. So this is called long skip connections, and they often exist in architectures that are symmetrical, where the spatial dimensionality is reduced in the encoder and then gradually increased in the decoder. and the output and input are of the same spatial dimension. So the height and width are the same. Or in case of 1D, then the number of features in the input and the number of features in the output is the same. So it has a U-shaped architecture. And basically in the encoder, we go down just like we do always. Then we have the bottleneck, and then we just concatenate symmetrically to the across the layers. So basically in the decoder, the number of channels is increased. And this is very popular in segmentation tasks or image denoising tasks, right? And it's quite popular today in a lot of medical applications, so machine learning for healthcare, especially when we care about segmentation. And UNet are quite popular, so take a look if you're interested. It's based on long skip connections. Okay, now the final topic of this tutorial is hyperparameter tuning. So this can be a very cumbersome process, and we have a lot of hyperparameters, especially when we use more complex architectures. And the question we ask here is, how do we tune them wisely, right? And what we do usually is called babysitting. I'll talk about it in a minute. So basically we just pick some hyperparameters by intuition, see if they work, then change them, and so on. Now, hyperparameters can have a huge impact on the accuracy and stability of the network, and there are maybe some optimal values that we are as the designers are not aware of because we did not consider to look in that direction. So maybe there are other approaches that can be utilized to find a better set of hyperparameters, right? So examples of hyperparameters is the number of hidden layers, learning rate, type of activations, how we initialize the weights, dropout, batch size, and so on. And we have a lot of them. And usually, to understand if something works, we look at the optimization metric or the task objective. So, for example, classification accuracy, or for image generation, we use like FID or the reconstruction error for autoencoders. And we determine whether this set of hyperparameter works based on this objective. However, sometimes we also care about stability. So stability is something that we can see by how the loss goes down. So if it's very noisy and does not go down smoothly, then maybe we picked some wrong hyperparameters. So for example, the learning rate is too high. So it's not only the final performance that we care about, so keep that in mind. Now we will discuss 4 tuning techniques for hyperparameters, and now we can automate the process with Optuna and PyTorch. But let's first start with the general techniques that we have, and why not we should use them. So the first one is called babysitting. So this is what we all do, right? Especially at the initial runs of our designed model. So we need to understand where the wind blows, right? So this is trial and error, and it's 100% manual, and this is what most of us are doing, especially at the beginning. And as you become more skilled, so as you gain more experience in deep learning and more experience with certain architectures, then you might gain some intuitions. Intuition what should be the range of values that you should test, but it usually can cost us a lot of time, and sometimes we can miss because we haven't considered looking at the very extreme areas of the search space, right? And this meme, I think, depicts the process quite clearly. So this is what we usually do, right? So watching a model train. So we take a look at the loss and then decide it's good, it's bad, and stop the run or wait for it to end. So another technique is called grid search. And grid search, it's a systematically testing of values for each hyperparameters. And basically you decide on a grid for each hyperparameter you want to check, and then you just loop over all your options, right? So you can decide, for example, that you want to check what is the effect of the batch size. So you choose like between 10 and 100 with the steps of 20. So that means that you will train your model 5 times. So the idea is to search for all the possible configurations. So here's an example. So here in this case, we iterate over the all possible learning rates, batch sizes, hidden units, and NLR. So a lot of loops, a lot of for loops, right? And this means a lot of models that are going to be trained. Now, the advantage of this method is that it maps the problem space and provides more opportunity for optimization. We can parallelize everything, right? And the problem with that is that it can be very slow, right? Especially if you have a lot of hyperparameters. It does not consider the history. So if your model diverge at learning rate of 1e-2, it will probably diverge at 1e-1 as well. So, and you still run this trial because there is nothing stopping except for the nonce or whatever stops the run, right? And of course, the curse of the dimensionality. So the more dimensions we add, the more hyperparameters we add, we will have to wait a lot of time. And it does not focus on areas of higher benefit. So if there is a very bad area of the search space, so for example, several combinations of learning rates and batch sizes, we will still run these experiments even though there is nothing promising about them. Okay, so when you should use grid search, so if you must report all the hyperparameters, so for example, you are writing a paper and you must report the values, then you can't avoid grid search, right? But otherwise, don't use grid search for deep learning. So what can we use for deep learning? We can use random search. So random search, instead of going systematically over all the possible values, we can just randomly sample values. Now, it was found that testing randomized values of hyperparameters is actually more effective than manual search or grid search, and it covers more areas of the search space, right? So as a rule of thumb, don't use grid search if your searching space contains more than 3 or 4 hyperparameters, and instead use random search, which provides really good baselines for each searching task. So maybe random search will come up with an interesting combination of hyperparameters, and then you can manually take it from there to grid search or manual tuning. Now, according to the study, it provides higher accuracy with less training cycle. So let's say you allocated 2 days for hyperparameter tuning. In the range of these 2 days, random search will probably come up with better combinations of hyperparameters. And of course, this depends on the number of hyperparameters, and if they are very large, so random search is the way to go. Now, similarly to grid search, the results are probably unintuitive. It's difficult to understand why hyperparameters were chosen, and of course, there is no history here, again, and we don't include any history. So how we can apply random search? So just the same set as before. You define a maximum experiments you want to run, and in each experiment you just randomly sample values, hyperparameters, and then run and train results. Now this is not systematic, so basically we can get combinations of hyperparameters which are different between iterations and are not close to one another, so this can lead to maybe more promising results. So keep that in mind. So in deep learning, we usually use a random search when we want to tune without something more sophisticated, like what we're going to talk about now. Now, the final idea we're going to discuss is called Bayesian optimization. And the idea is that we can actually try to predict the metrics we are trying to optimize from the hyperparameters configuration. So Bayesian optimization suggests the following idea. Let's start with some hyperparameters. Then as we go on, we will build a model that will model the probability of, given the hyperparameters, what will be the validation accuracy, for example, for classification. Now, this may sound a bit difficult to implement, but don't worry, we have frameworks to do this. And it's a very smart idea, right? Because if we can predict what will be the accuracy, then we can look at more promising areas. So this is what you will probably do if you are babysitting the model, and then you see that there are some combinations that work better. So you will manually search around them, right? But we can actually do this automatically with some framework. So the idea is that it trains the model with different hyperparameter values, observe the functions generated for the model by each set of hyperparameter values, and we do this over and over again. Each time we select hyperparameters that are slightly different and can help plot the next relevant segment of the problem space. So basically, this model that we built helps us find promising spaces to search in. So it was found that for practical applications, the results of Bayesian optimization result in significantly higher accuracy compared to random search, but still we don't have any explanation for why they work better. Now, Optuna, which is a framework that integrates nicely with PyTorch and with Scikit-learn, and we can use it to do this Bayesian optimization. So we just run it for some time you decide, and then come back and see what worked best. So just send and forget. So it works like this. So we build the model. We start from a random search. So we initialize the search process with some random sampling of hyperparameters. And then we train the model, and then we update our model, which predicts the accuracy from the hyperparameter. So as we progress with this model updating, you will see that the accuracy gets better because we search in more promising search spaces. Now, before we talk about Optuna, I want to have a summary of all the approaches that we have. So we have babysitting, grid search, random search, and Bayesian. So for classical machine learning, all of them work well. And we can use any of them that you want. For deep learning, so babysitting and grid search are not recommended because training the deep models can take a lot of time and we don't want to wait that much. So the complexity, of course, for grid search is high because a lot of hyperparameters to search. And if you are babysitting, so it's just you as humans, so so the patience that you have, so it usually, I don't know, it's low. So this is why the cost is low. Now, history is considered when you are babysitting because as humans, you probably have some memory, so you can remember what worked well and what didn't work. Grid search, of course, tries everything. There's no history considered. Now, for random search, the cost is lower than the grid search, but it does not consider history. So it is applicable for deep learning. And Bayesian, of course, it's applicable for deep learning. It has lower complexity than random search, and it does consider history. So bad areas of the search space will not be visited again. Now, there is a framework called Optuna that integrates nicely with PyTorch and Scikit-learn, which we can use. Now, I'm not going to cover this in this video, so I have a separate video for Optuna because I want to delve into the details of Optuna a bit more deeper. So I'll just give you the gist of it, and if you're interested, you can watch the video on Optuna. So the idea of Optuna is to help us find more promising search spaces by using Bayesian optimization. So you can see that Optuna, you can see each dot here is an experiment. So you can see that when we use Bayesian optimization, we look at more promising search spaces, right? So you can see more dots near the minimum. Now, you can see that when we build this model that predicts us the accuracy given the hyperparameters, we can actually start training, and if it's not promising, we can just discard the trial. So just stop the trial and not waste any more time on it. So we can actually prune trials, and Optuna provide us with this feature. Now, here is an example of the output of Optuna. So remember that we initialize with some random search. So you can see that the accuracy at the beginning will be low, so 9%, 15%. But as we go along, you can see that Optuna starts pruning unpromising trials. And already at trial number 20, we reach around 94% accuracy. Right, and finally, a lot of experiments are going to be pruned, and the output of the Optuna will give you the best trial and the best hyperparameters. So what you can do is just take them as is, or just now manually search around these values, right? So if it tells us to use Adam with this learning rate, so we should look around these areas, and Optuna also helps us understand which hyperparameter was important for the optimization objective. So if you optimize the accuracy, you can see that the number of units and the learning rate were very significant for the output, for the final performance, right? And it can also tell you, it can also plot you the search space where it looked and how it affected how it mapped the values and the resulting performance. So it's a very nice tool to help us understand where to look for. So if you're interested, this is in a separate video. And that's it for this tutorial. Thank you for watching, and I'll see you next time.